Hi everybody. Okay, we're going to learn how to balance redox reactions now. So we're going to start off with just a simple example, straight up redox, nothing funky about it. So we're going to take this reaction right here. Silver ions plus magnesium yields solid silver and magnesium ions. Okay, so if we take a look at this thing, we got to figure out how are we balancing it. There's a couple steps that you want to go through first. Before you can get there, you want to decide, like, is this a redox reaction? Obviously it is, because I'm showing you how to balance redox, but if you're just looking at something and it says balance the equation, first figure out if it's redox or not. So let's start by looking at our reactants. We have an ion and we have this magnesium right here, no charge on it. This must be elemental magnesium, which means its oxidation state has to be 0. Silver has a plus charge, and we know that any ion, its oxidation state is equal to its charge, so this has an oxidation state of +1. All right, coming over here, look at our products. This thing is elemental silver, must have an oxidation state of 0. Magnesium is an ion, so its oxidation state is equal to its charge, 2+. Great. Okay, so we see some changes in oxidation states. Yes, this thing's going to be redox. Let's figure out what's oxidized and what's reduced. So if we start with silver, we're going from +1 to 0. What's the only way it could get there? So if I'm going from something positive down to 0, I am reducing my charge. I must gain electrons in order to have my charge go from something positive down to something more negative. So if we remember our mnemonics, oil rig, or Leo the lion says grr, this thing is reducing its charge. It must be gaining electrons to move down, so it is being reduced. It's reduced because it's gaining electrons. So that means that magnesium, which is going from 0 to +2, is losing electrons because it is going to a more positive oxidation state. So therefore magnesium is being oxidized. It has lost electrons, it is oxidized. So now that we know what's happening to the species in our reaction, we're going to use this to help us write out what's called our half reactions. So remember, you can't have one without the other. Something can't be oxidized without something else being reduced. So when we call these our half reactions, it's the half of each of the whole thing, right? You have your oxidation, half of it, and then you have your reduction, half of it. So we know that the thing that's being oxidized is our magnesium. So I'm going to write out just what's happening to the magnesium first. So Mg is going to form Mg2+. Great. For reduction, my silver ion is going to form elemental silver. So these are my two half reactions that I'm going to start with. So to balance redox reactions, your very first step is write separate equations for your oxidation and your reduction half reactions. Now comes your second step. For each half reaction, you're going to start by balancing your elements. So this is step 2A, whatever you want to call it. So if I look here, I have one magnesium, one silver, one silver. So that part, as far as we're concerned, is balanced. We have the same number of atoms on each side at least. So now I move into step 2B. I'm going to continue balancing each of my half reactions by balancing charge. To do that, you add electrons to your half reactions, because remember, redox is all about a transfer of electrons. So let's figure out how many electrons we need to add and where we need to add them. So let's start with oxidation. In oxidation, you have something that is losing electrons. So my magnesium is going from something that has no charge to it to something that is positively charged. I go from an oxidation state of 0 to +2. So how many electrons did I have to lose to get there? I had to lose 2. So what we're going to do is write a +2 electrons on this side of our reaction equation. We became an ion by losing 2 electrons. So now let's think about reduction. So on our reduction, how did we go from being an ion to being elemental silver? Well, I had to gain electrons. How many did I have to go to gain to go from +1 to 0? Well, I had to gain 1 electron. So now I've balanced the charge of each of my half reactions, and now I can move on to my last step, adding the two together. So step 3 for simple redox reactions is adding the two together and then just figuring out if I need to do any multiplication, I need to do any canceling, yada yada. So if I take a look at this, I have 2 electrons in my oxidation. I only have 1 that I'm dealing with in my reduction, which automatically tells me I have to multiply this thing out. My charge won't be balanced if I'm transferring 2 electrons here and only 1 here. That doesn't work. Conservation of charge, conservation of all of that stuff doesn't work. So I'm going to take this entire reduction equation and I'm going to multiply it by 2. So when I do that, I'm going to move this and write it down right here. So I have Mg plus Mg2 plus, or yields Mg2 plus 2 electrons. If I multiply this by 2 and then write it down here, what I end up with is I have 2 Ag plus 2 electrons yields 2 Ag. And now I'm going to add these half reactions together to get my full reaction. And when I do that, I bring everything down on my reactant side. Mg plus 2 Ag plus 2 electrons yields Mg2 plus 2 Ag plus 2 electrons. Last step now is to cancel anything that is like. So I have my 2 electrons on both sides, which is good news because I forced it to be that way. But the reason why I want this is so I can cancel those electrons out. They're being used in this transfer, so I can boom, boom, cancel, cancel. And my final reaction, my balanced redox reaction, is going to be Mg plus 2 Ag plus yields Mg2 plus 2 Ag. Yay, done, balanced. All right, now let's kick it up a notch. So let's say that we don't just have a simple redox reaction that we're dealing with. Instead now, we've taken our substances and we have placed them, we have used some sort of acidic or basic solvent to get our species to dissolve. This makes balancing the redox reactions a little bit trickier because you have to deal with the fact that you have excess hydrogen or excess hydroxide or water in your system now. So let's start out by figuring out how we can balance something that's under acidic conditions. So for this thing right here, I have dichromate, Cr2O72 minus. I'm adding to it sulfur dioxide, SO2, and I'm producing the chromium 3 plus ion and the sulfate polyatomic ion. So I want to balance this reaction, but the first step is to do the exact same thing that I did in the previous one and figure out what's being oxidized, what's being reduced here. So if I take a look at my dichromate ion first, I know that the total charge of this thing has to add up to 2 minus because it's a polyatomic ion. The charge of the ion must be the same as the individual oxidation states of the atoms must add up to be the charge of that ion. So every oxygen is going to have a minus 2 oxidation state. And I have 7 oxygens, so that's going to contribute a total of minus 14. I need the total compound to be a charge of 2 minus, and I have 2 chromiums to get there. So what that means is my chromiums have to add up to a charge of plus 12. If they do that, if this total thing is a charge of plus 12, then plus 12 minus 14 gives me an overall charge of minus 2. So if I have 2 chromiums, how can I do that? Each chromium must be a plus 6 oxidation state. Okay. So now I'm going to move on to the sulfur dioxide. All right, so this thing has no charge associated with it. So each oxygen must have a minus 2 oxidation state. I have 2 of them for a total charge of minus 4. So that means each sulfur must be plus 4 in order to get that thing to cancel out. Awesome, great. Okay, chromium, 3 plus. It tells me that because it's just the simple ion. And now we've got sulfate here. Each oxygen must contribute a minus 2 for a total of minus 8 because I've got 4 of them. The whole polyatomic ion needs to have a charge of minus 2, which means my sulfurs have to contribute a charge of plus 6. And if I only have 1 sulfur, it's going to have that plus 6 all on its own. Okay, now let's figure out what was oxidized, what was reduced. So if I take a look at chromium, I'm going from plus 6 to plus 3. All right, how did I get there? Well, I'm reducing my charge. I'm going from something positive to something less positive. So that means that I must have gained electrons to get there. Chromium has been reduced. So my reduction half reaction is all about chromium. Cr2, O7, 2 minus, going to Cr3 plus. Great. All right, now let's take a look at the other stuff we've got going on here. My oxygens do not change oxidation state at all, but my sulfur does. I go from plus 4 to plus 6. So I'm going from something less positive to something more positive. So how could I have gotten there? Oh, I must have lost electrons in order to increase my positive charge, so I have been oxidized. So my oxidation half reaction is all about my sulfur. SO2 yields SO4 2 minus. All right, so remember that we're in acidic conditions, right? So we should have extra hydroxide or extra extra hydrogen floating around in solution. So when we're going to start these, they start the exact same way as the previously balanced ones, but now that we're under acidic conditions, what we're going to do is balance our elements first, except for hydrogens and oxygens. So let's take a look at our reduction half reaction first. So in our reduction half reaction, what you should notice is that I have 2 chromiums on the left, only 1 on the right. So how can I fix that? Let me just add a coefficient of 2 right there. Great. Okay, now that part is good for right now because I have to balance everything besides my hydrogens and oxygens. Okay, and then what I can do is go over and look at this side right here. All right, to balance any atoms, I have 2 oxygens on the left. I have 4 on the right. So how can I deal with that? Well, I can make this thing a 2. All right, but if I do that, now I change my sulfurs again, right? Uh-oh, so I would have to add a 2 over there. But no, it changes my oxygens again. So here's what you want to think about. What's the smallest number that I can make both of these that's going to get my sulfurs to, like, be chill, right? Just balance out, be good. Well, I'm at 2 right now. If I change this to a 3, that's going to give me 12 oxygens. Okay, so how can I get to 12 oxygens over here? Well, if I multiply this by a 6, that's going to get me to 12 oxygens, but it's going to give me 6 sulfurs. Uh-oh. Okay, so to start balancing this reduction reaction right here, I see that I have 2 chromiums on the left, which means I need 2 chromiums on the right, and all I've got left is oxygens. If I come and take a look over here, my non-oxygen atoms, sulfur and sulfur, are balanced. I have 1 of each, so now I can move on to dealing with the oxygens. Okay, so to balance oxygens, the trick is we're going to add waters to get those things to balance out. So if here in my reduction half reaction, I see that I have 7 oxygens on the left-hand side, I'm going to balance that out by adding 7 waters to the right-hand side. So that means I now have 7 oxygens. I'm going to rewrite this oxidation half reaction up here so I can give myself a little bit more space on this page right here. Okay, so I'm going to start balancing things out by adding waters to get my oxygens to balance. Cool, donezo. All right, but now I've added hydrogen to the mix, right? So my next step is to balance hydrogens by adding H pluses. Remember, we're in acidic conditions here, which means it's fine to be adding H pluses because we know we should have extra H plus in excess because we are in an acidic condition. Our acids means you have dissociated H pluses in solution, right? So to balance this out, on the right-hand side, I have 14 hydrogens, so I'm going to add 14 H pluses over to this side of the equation. Squeaky marker. All right, so now that gets my hydrogens to be balanced out. Cool, great. Next step, now I can go back to where I was before in my like regular redox reaction balancing. Now I work on balancing charge. So to balance charge, I add electrons. So if I take a look on the left-hand side, I have 14 H pluses, so 14 positive charge, and then I have 2 negative charges contributed by this ion. So overall, I have a charge of 12 plus on this side. On the product side, I have only the chromium contributing to my charge, which is giving me a charge of 6 plus. Okay, so to balance this out, I know that I'm reducing here, so I must be gaining electrons in this process, right? Which makes sense because I need to go from plus 12 to plus 6. And the only way for me to do that is by adding 6 electrons to the reactant side of this equation right here. Okay, so this is my reduction half reaction. Now I'm going to work on the oxidation half reaction up here, and then we can, work on continuing to balance charge and atom together. All right, so to balance oxygens, what do? I have to add waters. So I've got 2 oxygens on the left, I've got 4 on the right. So to balance that out, I add 2 waters over to this side. Now I got to deal with balancing hydrogens, that comes next. So if I've got 4 hydrogens on the left, I need to add in 4 H pluses on the right. So start by balancing oxygens by adding water. Then balance hydrogens by adding H plus for acidic conditions. Now we move on to balancing charge. Overall charge on the left is 0. Overall charge on the right, I have 2 minus here, 4 pluses here. That's going to give me a total charge of plus 2. Okay? All right, so how can I get a plus 2? Well, I know that this is my oxidation reaction, so I have to be losing electrons. So how many electrons do I lose? 2, and they have to go on this side because I'm losing them. So I'm going to add 2 E minus over to this side of the equation. Okay, now let me write up my reduction half reaction. I have 6 electrons plus 14 hydrogens plus dichromate ion yields 2 chromium 3 plus ions and 7 waters. Okay, so normally what's best to do when you're doing redox reactions is lining up your arrows so you can see half and half to make it a little bit easier, but because I'm kind of working in a small amount of space here, I'm just not going to line those up for me for right now. Okay, So how can we fix this? All right, let's see where our electrons are at. We added electrons in, now we need to multiply and add things up together. All right, I've got 6 electrons in the reactants and only 2 in the products, which means this is the one that I have to fix. How do I fix it? I can do that by multiplying this entire reaction by 3. Okay, so that's going to get me 6 H2Os. Let me write this a little bit smaller, help us out. That's going to get me 6 H2Os plus 3 SO2 minuses. And then I'm going to get 3 SO4 2 minuses plus 12 H pluses plus 6 E minuses. Okay, so I'm just going to take my my oxidation reaction and move it down here after I've multiplied to make things a little bit easier. So now this is gone, and now I can add things up to get my final balanced redox reaction. Whew. All right, coming straight down, I've got 6 electrons on this side, but those 6 electrons on this side are going to cancel out with these 6 electrons on this side, so I'm going to cancel those right away. Okay, if I take a look at hydrogens, I've got 14 up here and I've got 12 down here, so that means that all of these are also going to go away, and I'm going to be left with 2 H pluses left over. I've got 6 waters on this side and 7 on this side, so I'm going to cancel all 6 of those waters, and I'm just going to be left with 1 over here. And now I can work on adding down. So I have 2 H plus 3 SO2 plus Cr2O7 2 minus. These are all of my reactants. This is going to yield 2 Cr3 plus H2O plus 3 SO4 2 minus. Whew, just enough space. All right, so now that I've multiplied, added straight down, canceled all things that are like, this is my final redox reaction for the this reaction that we started with in acidic conditions. So balancing in acidic conditions, extra step, balance your elements first, then balance your oxygen by adding water, balance your hydrogen by adding H plus, balance your charge by adding electrons, and then it's pretty much the same. That's great. Okay, everybody take a deep breath, pat yourself on the back, get a quick little stretch in, because immediately up next, it's time for basic conditions. All right. So this follows a very similar pattern to what we've been doing, where our first step is figuring out what the heck is going on. All right, so let's start by figuring out what's being oxidized and what's being reduced. So this one's nice. We have I minus right here, which means we know its oxidation state is going to be -1. Thanks, ion. All right, and then next up, we can deal with our compound. So rule, hydrogen's in here, which means this thing's going to have a +1 oxidation state because that's our most important rule. Each oxygen needs to have a -2 oxidation state. So what we're looking at right now is a total of -4 + 1. We know that our overall compound has to cancel out to be neutral, so our chlorine's got to be the one we work with to get things to balance out. Overall, right now I have a net charge of -3, which means our chlorine has to be a +3 charge to get this to be overall be neutral. All right, now let's take a look at the product side. So I've got elemental chlorine over here, Cl2. It's going to have an oxidation state of 0. I see I have a hydrogen, that must be a +1. My oxygen must be a -2, which means I have iodine to balance this out. Right now I have a net charge of -1, which means iodine must have a total charge of +1 in order to get that compound to be neutral. Okay, so what's the dealio? What's going on? What's being oxidized? What's being reduced? So if I take a look first at my iodine, it's going from a -1 to a +1. All right, cool. So how could it get there? I'm going from something negative to something positive. So that means I must be reducing my charge. It means I must be losing my electrons to get there because I'm going from something more negative to something more positive. So that means that our iodine must be oxidized. So this thing is losing its electrons. Okay, next. Looks like hydrogen doesn't change. Looks like oxygen doesn't change. Oh, but chlorine does. So chlorine's going from +3 down to 0. So this thing is being reduced in charge. I'm going from something positive down to something more negative. So in order to get there, I must be gaining electrons, reducing my charge. So Cl must be reduced. Okay, so let's write out our half reactions. I am going to put let's put the oxidation half reaction on here, and then I'll put the reduction half reaction on the larger whiteboard. So for oxidation, I'm dealing with I minus producing HiO. And then for my reduction half reaction, I am dealing with HClO2 producing Cl2. Okay, so let's deal with our oxidation half reaction first. First step, we're going to balance out any element that's not a hydrogen or an oxygen. Cool, done. So easy. All right, next step, you're going to follow the same pattern. You are going to balance out your water or your oxygens by adding waters. So I have an oxygen on this side. I need an oxygen over here. So I'm going to add a water to get that to balance. And now I'm going to balance my hydrogens by adding H pluses. So I have 2 hydrogens over here, 1 hydrogen over here. So I'm going to add 1 H plus over there. Okay, but remember, we're in basic conditions. No, why are we doing this? Basic substances are not known for having free hydrogens. That's because right now what we're doing is we're just balancing things out. At the end, we will end up having excess hydroxide, which is going to be help us define our basic system. But for right now, all we have to focus on is just balancing out our hydrogens first. I promise things are going to work out. You'll see it in the next step. Okay, so now that I've got those all balanced, let's deal with balancing with our charge, adding in our electrons. On the left, I've got a minus charge over here. On this side, I've got a plus charge over here. So how can I make these things cancel out by adding electrons? Well, this is my oxidation half reaction, which means I must be losing electrons, so they must appear over on this side. So it would make sense that if I need to get from a +1 and balance my charge out to be a -1, I have to add 2 electrons over to that side. That's going to get me an overall net charge of -1 on both sides. Okay. Now that I've done my oxidation half reaction, let's take a pause. Let's go deal with our reduction half reaction. Okay, so I have HClO2 and Cl2. Okay, my non-hydrogen or oxygen elements, chlorine, chlorine, I gotta balance those out first. So I'm going to put a 2 in front of that thing right there. That's gonna help me out. Okay, now I gotta deal with my oxygens. I've got 2 over here. To balance those out, I must be adding water. So I'm going to add, oops, hold on one second. I forgot I put a coefficient of 2 right here. So I needed 2 oxygens initially, but with that 2 in there, it means I need 4. So I'm going to add 4 waters over to that side, and now my oxygens are balanced. Cool. Okay. Now I got to deal with balancing my hydrogens. So I have 2 hydrogens on this side. I have 8 hydrogens on this side. So I got to deal with that by adding 6 more H pluses to that side right there. Okay, great. Now that my atoms are balanced, I deal with charge. Overall, my charge over here is 6 plus. My charge over here is nothing. So I got to cancel out that 6 plus to make it an overall net charge of 0. So to do that, I add 6 electrons over to this side. Oops, can't really see that. There we go. I add 6 electrons over to that side. Okay, so now if I take my oxidation and my reduction reactions and I put them close together, you'll notice that I have 2 electrons in my oxidation and I have 6 electrons in my reduction. So I have to make those things balance out. How can I do that? I can multiply this thing by 3. When I multiply this reaction by 3, I end up with 3I minus plus 3H2O yields 3HIO plus 3H plus 6E minus. Great. Now I'm going to recopy that onto this one right here so I can take a look at them right next to each other. So here's my oxidation half reaction. 3I minus plus 3H2O yields 3HIO plus 3H plus 6E minus. All right. Hello? There we go. Okay, so now I can deal with my next step, which is adding these things up together. All right, so 6 electrons and 6 electrons cancel. Boom, boom. I am not going to cancel anything else besides my electrons just yet. So, and you'll see why in just a second because we're in basic conditions. Okay, so now let me add up, write our next line on here. 2 HClO2 plus 3I minus plus 3H2O plus 6H plus. Ooh, I'm gonna run out of space. It's okay. We can do this, everybody. Let me just write it smaller. I need like 6 whiteboards. 2 plus 6H plus 3I minus plus 3H2O yields Cl2 plus 4H2O plus 3HIO plus 3H plus. Okay, cool. All right, there we go. Now it's tiny, but it fits. Yay! All right, so remember that we are in basic conditions here. So here's what we're going to do to deal with that. For basic conditions, once you get to this part, what you're going to do is add the same number of hydroxides as your H plus ions. So if you have hydroxide reacting with H plus, what's that gonna make? Well, it's gonna make water, and that's fine. You can make water and then have leftover hydroxide. That will put you in basic conditions. So for basic, you just have that one last step. We're gonna add in some hydroxides here. Okay. So if I take a look at my reaction, what I notice is I have 6H plus on this side and 3H plus on this side. So net, what that means is I have no H plus over there and I've got 3H plus over here. Okay, cool. So if I have 3 H pluses, I need to add enough hydroxides to react to produce water to neutralize all of this H plus. And I can do that by adding 3 OH minus since they react in a 1-to-1 ratio. But whatever you manipulate one side of the equation, in doing, you have to do the other one as well. So I'm going to add in 3 OH minuses over there. And now what I know this is going to do is this is going to make 3 waters, 3 H2Os. Cool. Now I have to finally do my very last step, which is my final cancel and sum one more time. So let's analyze what we've got here. So overall, I've got 6 waters on this side of the equation, 3 here, 3 here, and I've got 4 over on this side. So that means that all of these waters are gonna, boom, go away. And over on this side, what I'm gonna be left with is 2, because 6 over here, 4 over here, net, I've got 2 left. Anything else that cancels out? No. So now I can finally do my last sum. to get my final overall redox reaction equation. Okay, I'm gonna try and write as small as I possibly can. 2HClO2 plus 3I minus plus 2H2O yields Cl2 plus 3HIO plus 3OH minus. And now, look at that, we've got extra hydroxide showing we're in basic condition. My net charge on this side is 3 minus, and my net charge on this side is 3 minus as well, thanks to that iodine. So this is my final balanced redox reaction equation for basic conditions. All right, now you're gonna get some practice.